Okay, in the fourth tutorial of using pyMS-Vis, I want to get into some advanced topics. So the plan for today is just to load some files, take a look at where some of the outputs, the HTML and the CVS file live, play around with some of the other options, for example, the off by Win Dalton search function, and then I will show you a little bit of the code and where you can make some adjustments to save some time and copying and pasting. So I'm going to start off today by loading some data that was deconvoluted. This is going to be data that is middle down data. So these were proteins that were digested in GluC uh, and run on a LCMS or Retrap Fusion. The data that I'm interested in looking deeper into is modifications on the first 50 amino acids of histone H3. So I'm going to load the data. What you can do is you can load them individually, but why would you want to do that? You can go ahead and select all the files that you want to open. Here I'm going to load some TSV files, and I'm going to search, or the feature map I'm going to use is the MS1FT. All right, so I'm just going to name these, 1, 2, 3, 4. There we go. To indicate that they just come from different conditions. Uh, Last time I had them all in the same group, so you can kind of see how the data was aggregated, and you got averages and standard deviation if they were all from the same experimental condition. Here, these are all 4 different experimental conditions. So if I click Process File, then we get this screen. So as I mentioned earlier, it auto-populates these H2A masses, but because I'm interested in the first 50 amino acids of H3, I'm going to put in some different masses that I'm interested in. What these masses are, they are all unacetylated, multiply methylated. So you'll see that there's a 14 Dalton increase as you go on. Here, the mass tolerance, I'm just going to set this at 20 to search for these masses, plus or minus 20 ppm. When I went back and I looked at this data, I realized that the instrument was off by about 12.5 part per million, so all my masses were off by that. So I want to correct for that so that I can get better resolution on what I'm looking at and picking out. It's worth noting that histones are highly modified, and especially H3. Methylation is 14, acetylation is 42, but if you look more deeply in that, trimethylation, which is 14 times 3, is also 42, but it's 42.05-ish. Acetylation is 42.0105, so that's a 35 millidalton difference. So that's going to be important a little bit later on. So going into it with as precise mass measurements as possible is the way to go. Right now I'm going to leave the off by 1 Dalton search, and then I'll show you what happens when I enable it later on. So I'm just going to see what this gives me. There are about 24,000 scans, so a lot of data to go through, but it does so pretty quickly. If I calculate everything, so what am I looking at? So this is the data. that is generated from just searching all of these masses. I'm looking at the entire LC run, so I'm not filtering any of the data. So all of this data that is the relative intensity of the different masses, it's the accumulation of all this information. Now, as you can see here, I have my conditions 1, 2, 3, 4 all different. And so what happens is the program will color code the different conditions, and you can kind of see how things are changing across the different masses. So if we're to zoom in here and look at the 4 data sets, okay, so you see relatively similar stuff, meaning that um, there is some interesting masses eluding, some a little bit before the others, and you can kind of see that there's a little bit of difference between the elution profiles of these masses. So when I look deeper into this, it actually turns out that the column is doing a great job separating based on acetylation states. So this is a zero. I found out that this is a 0 acetyl, 1 acetyl, 2 acetyl. So as I mentioned, the masses I put in are for no acetyl but multiply methylated histone H3. Why are we getting acetylated masses in our outputs? Well, the reason for that is some of the masses are very similar, both very similar at some point. So just to illustrate that a little bit, if you see here, so you can have a mass that is 0 acetyl, 0 methyl, be this, and then as you go on to the 3 methyl mark, you have this mass. Well, 1 acetyl, 0 methyl is this, and you can see that they're very close in mass, but they are off by some value, so they're not exactly the same, so we can use that. However, you can see as I color coded here, these are masses that are very similar to one another. And in fact, in some cases, you have, some masses that are that pop up that have the same what basic unit, but the finer detail in the masses is changed. So here you can see this 0.16 past the decimal point, 0.1254, 0.0908. So what's happening here is that because the program is searching for masses based on your search criteria, if you're not careful, you can pick up other things that you may not be interested in. So how do you rectify that? Well, if you see something like this going on, you can go in and tighten your mass search. So just to show you what happens if I change the mass tolerance to 5 ppm, what should happen is it starts to eliminate some of those masses that were similar but out of those bounds. Okay, so this is the new result. If we were just to again look at that first the first sample data, let's see, let's do this. Okay, so you can see here now that the species in the first data set, there we go, apples to apples. You can see that we've now eliminated these masses from our quantitation and we're only focused on the monoacetyl because we have the appropriate search parameters to really, you know, uh, limit what we're looking at and quantifying. Now, why is this super important? just that difference in ppm selection changes the quantitation dramatically. So you can kind of see that up here versus here, right? In this quantitation, all of these masses are going into uh, all these masses are going in to contribute to the different intensities that are summed up and averaged. Well, if you're thinking about these masses and you're like, oh, I'm looking at only the unacetyl, right? Uh, well, that's not what you're looking at, because you're actually looking at masses that happen to be very similar and actually aggregated because of your search conditions that are zero acetyl, one acetyl, and two acetyl with multiple methylations. This is obviously the correct quantitation of the data that shows only the monoacetyl being selected. And so if you were to go through each of those other files, you'd actually see, zoom in, you'd see that it is indeed one peak, whereas all these other ones, they are three. So a word of caution, the importance of selecting masses based on, you know, stringent searching, and also kind of at least having some idea of what you're looking for, and what is the appropriate search conditions for your masses of interest. Okay, so there is a phenomenon that happens when you deconvolute data, where the search alg or the deconvolution algorithms do not correctly select the monoisotopic peak. It's basically you're off by 1 Dalton. So this creates a problem with quantitation, because if you're off by 1 Dalton because of your algorithm, well, the mass is there, it's contributing to the intensity, but but you're not seeing it, right? Because it's outside of your search conditions. So I decided to add this functionality where if you click this button, what will happen is in addition to these masses that you're searching for, uh, 1.00235 will be added, uh, plus or minus your mass error tolerance. So it does not search a range. It searches exactly 1.00235 plus or minus your mass error tolerance. So this, I believe, will help with quantitation, because you're picking up more of the masses that you may have missed because of the deconvolution algorithms. So how does this change things? So if I leave these conditions the same and just click the off by 1 Dalton search, okay, so let's clean this up a little bit so we can kind of compare. All right, we'll do this. Okay, so this is with your masses and the one by off by 1 Dalton masses, and this is not. All right. Overall, um, the profile is somewhat similar between the two, right? But there are some pretty noticeable differences. So this is again, the zero acetyl, no methyl, 1, 2, 3, 4, 5 methyl, zero acetyl, zero methyl, 1, 2, 3, 4, 5. So this does not look like that, okay? So why is that? So if we were to zoom in here and here, we can see that the off by 1 Dalton uh, measurements or options, we're selecting more masses. We're finding more masses that meet the criteria. So here, this low abundant form for 5436.175. This is there's 1, 2, 3, 4, 5 found all in this region, whereas there's only 4 here. Okay, um, that's sort of an important finding, because if you look at the distribution, what's missing? So over here, we're missing this mass right at 4290. That's gone. And the quantitative, so we're missing some other things. Let's see here. These are all the same. These are all the same. So we're actually just missing this one. So I believe that's real. You can see that it kind of falls within the same envelope, the same kind of distribution, and it's missing here but present here. All right. And that's going to be true for some of the other uh, masses as well. So it's picking up more data that's real. All right. So, yeah, there we go. Okay. The other thing that was going to contribute to the differences here is that we are a little bit um, we're a little bit unrefined at this point, which means if you're to zoom out and take a look at some of these other spectra, okay, so we did not go into this limiting the retention time. So what does that mean? It means that all of these masses that may not be related to the masses we're interested in, that just are popping up because they meet our criteria, but they're out of our retention time window. They're being summed and added to this, so they're adding noise. So remember, when we do our static searches, that's great for sort of a crude view of what's going on. But what you really want to do is you want to go back and refine your search so that you're only considering masses and intensities that fall within an elution time that you're interested in. So I would not use this data for anything other than finding out the retention time of the masses we're interested in. Okay, so just like the other tutorials, what we want to do is we want to go back to our search parameters. We want to choose dynamic. And now, because I know where the retention times are, okay, so this is the time. So my sample one, I know that the retention times are between this for the unacetyl. Okay, so let's do this the same, 5 ppm, 12.5. And let's just kind of compare, let's just do the off by 1 Dalton search. Um, that's interesting. Um, oh, probably need to search for the actual masses that we're interested in. So one thing to note is that when you do switch from static to dynamic, what happens is it does reset everything you've put in. Maybe I'll change that later. So let's find these other. Okay, all right. Okay, there we go. So these are the masses. These are the unacetyl multiply methylated masses, and then that's all the same. So let's get that going. Okay, much better. And then let's go back over here. Let's do the off by 1 Dalton search. Okay, so let's clean this up a little bit, make it easier to compare. Okay, so now we're comparing them. This is going to be, um, so I've flipped it. So this is our normal search. This includes off by 1 Dalton. You can still see the 5th methyl form is quite a bit different between the two. But now what we're doing is we're quantitating things correctly. So we're you can see that the masses that were selected fall within our window. Okay. Okay. And so we can see that here. Okay. So if we were to zoom in again, let's just kind of compare these. So these aren't that different. Here it looks like we're picking up some more masses in our off by 1 Dalton. And again, the ones that are being picked up, if you look over here, there's an orange and a red one that's missing here but present here. I truly believe that that's real data. You can see that it follows the. If you were to imagine this being, a sort of a total line chromatogram of a peptide or protein coming off, you would imagine this being an elution peak, right? Starts off low, peaks, comes back down. Um, so right, so you can search with this option and get a better approximation for your data. Okay, so that was quite advanced, but hopefully useful to some percent of you out there. Now, uh, every time you run the script, what happens is it will generate a file. Usually the output files live in the same directory as the Python script, but on my computer, it's moved elsewhere. So let me just find them and move them. Okay, I'm just going to move them all over here. Okay, so when you run it, it will just give you a CSV file or an HTML file, and it gives you outputs that are time stamped. So, and everyone is unique. So we can kind of go back and take a look uh, at some of these different files. And you can see, right, this was the first search we ran. This is the last one we ran. So all the data is saved. If you want to, you can easily export. Well, first of all, the bokeh plots are absolutely amazing. You can zoom in. You can really look at your data. If you want to save this as a PNG, you can click download. Yay PNG, right? And then there you go. You could plop it into whatever you want, which is great. So if you want the actual raw data, it's in a CVS, or CSV, CVS, CSV. So if we open it up, um, let's actually, yeah, let's do this. So if you open it up, you're gonna get two flavors of information. On the top here, these data represent the values that correspond to each value in the plot. Okay, so you can go and uh, remake this exactly with this data. So let's see here. So this was the 059. Let's open the same one so I can show you 059. I guess that's close enough. Oh. So this mass here, it's 4.8 abundance, and you can see that at 4.8. Here, that one is 11.8. 11.8. So that this is all the quantitation data. For some of you, it may be of interest to have the raw data. So what I've done here in the bottom part is for all the files that you've inputted, I have provided you the total intensity of all the peaks. So not just the relative intensity. Why could that be useful? Well, let's say that you're interested in these masses and the overall intensities across these different runs. You can just do something like this, where you can compare the overall intensities. Let's make this look better. Okay. All right. Okay. So, your intensities scale with overall protein load, and if you're wanting to ensure that, say, for instance, it's really important that you have similar intensities of your ions, of your peptides across different runs, you can use this to approximate that. You can tell here that there's an order of magnitude difference actually in some of these intensities between this run and this run here. So you can quickly get an idea of that, and uh, as an example of what you can do with this data. But yeah, this is all the total intensities for each of the masses that you've queried, in addition to the relative intensity. So some of you might find that helpful. Okay, what else for this tutorial? So, um, yeah, I think that's it for now. This has been a bit of a crude, sort of like whatever's on my mind, I'll talk about tutorial. If I have some time, I'll probably chop this up into different sections. But for right now, you have a taste of what you can do with the program, um, and yeah, and hopefully that's helpful for you. So until next time.